My somewhat hyperbolic title here, A Convenient Untruth. As you can see, the remainder, I'm going to talk about how measurement error can sabotage nutritional epidemiology and give you a little hint about what can be done about it. And I'm actually going to build on what Stan just talked about improving, or trying to improve the assembly line, as it were. Another reason I'm very glad to be able to speak to you today is because they don't let me out of the office to do much because I don't get to do anything, right? No, nothing, none. So, all right, so let's talk about nutritional epi for just a moment. What's our goal? Well, usually our goal is to relate dietary intake to some health outcome. And for many, many years, the measure of intake thought to be most relevant for most nutritional epi, not all, but most, is what's called usual intake. And it's defined here as the long-run average daily intake. Okay, your dietary recommendations aren't meant to be necessarily met every day, but set over time. These sort of things all the nutritionists in the room probably know, and anyone that has heard Iowa State University probably says, oh, it's those usual intake people again. But yes, it's us. But measuring that exposure is actually, you can think of it, it's actually pretty hard to do. Measuring someone's average intake over a long period, 1 or 2 years or more, if you're talking about cancer, where you have to, where it's the intake way back that might be important, is very challenging. And like it or not, we're more or less stuck right now, for the vast majority of all the things we want to look at, with self-report instruments. So I'm going to talk a little bit about self-report instruments. Katie Tucker is going to give a lot more in-depth stuff, I think. But in my mind, dietary assessment instruments kind of fall on this sort of spectrum that kind of puts weight on these two parts of usual intake. The long-run average part, I would epitomize with a food frequency questionnaire, whereas daily intake would be more of a 24-hour recall concept. And your other dietary instruments, self-report, are going to fall somewhere in the middle. Your 3-day food records, your screeners, these sort of things, are also going to be along that line. Now, I'm not going to talk too much about these things because Katie's going to do it, I think, shortly after. But food frequency questionnaire is what is going to be one of the ends of that spectrum, and FFQs try to capture long-term intake, and there's some aspects of FFQs that make them challenging to work with, but they keep getting used, and I think a lot of the reason has to do with the fact that they're inexpensive to administer. In fact, they may be the only feasible thing. They're, dare I say it, convenient to use in a large-scale cohort study. I think Katie may actually make another mention about how actually in some cases FFQs may be exactly what you want. You may be wanting to do to really assess episodic consumption that you can't do by looking at short-term things. At the other end of the spectrum is your 24-hour recall. The idea being that you only ask about what happened yesterday. You have a short-term recall, so it might be less cognitively challenging. The trouble with only getting 1 day is 1 day is not usual intake, so you need to have replicates to assess usual intake. And back when I was much younger and less gray, at Iowa State University, we worked a lot on developing ways to estimate usual intake distributions from 24-hour recalls with some statistical modeling. Now, they don't get used as much in big cohort studies because traditionally they've been interviewer administered and therefore very expensive to collect and code. Furthermore, when you start trying to go from nutrients that are consumed every day to more episodic consumption, that requires a whole lot more statistical work to actually get something useful from. All right, so I appreciate Stan breaking the ice here about the equations. Personally, I think that every time a statistician shows an equation, an angel gets his wings. So Stan, thank you for helping out, and I'm going to continue on. So I'm going to talk about truth and what we measure. Q. I'm going to call it Q. I'm not trying to bang on questionnaires, but that's just the notation that I'm used to. Roughly speaking, measurement error is nothing more than the difference between what you measure and what you wanted to measure. Okay? And it turns out that this measurement error structure of an instrument that you have under consideration, it arises from an interaction between the instrument itself and the population of the study. And Katie's going to tell you more about how that can impact things. What I'm going to talk about is from the statistical side, when we start talking about trying to look for, properly significant effects, if you ignore measurement error, what it's going to do. And what we're going to find out is, in contrast to what Stan was talking about, where people are finding stuff, finding significant results, in nutritional epi for a long time there weren't any. And John showed some of the other ones that when we started that you're not finding these associations. Well, why could that be? And measurement error may be part of an explanation for why you see a lot of these null results, because if you ignore measurement error, you can end up getting underpowered studies and biased results. And a lot of times, as you'll see, that bias is toward the null. So before I talk about, before I get anything very fancy, I'm going to talk about what's called classical measurement error. In this case, we're going to say that measurement error is completely random. It has nothing to do with personal characteristics. It's just random noise. And I'm going to institute these subscripts here, an I for individual and J for replicate, to kind of get this idea that if you were to take an instrument and you apply it several times to the same person, you're not always going to get that person's truth if it has a random error. There's going to be some extra error. Okay? Now, if you didn't have this error and you plotted Q against T, you get a nice 45-degree line, like Stan was showing earlier. But you don't, because you have this extra error, and so your lines start, your dots fall off the line. Okay? So you have not a perfectly correlated instrument anymore. Now, when Q has a classical measurement error structure, it's said to be a reference measure for truth, for what you wanted to observe. And it turns out that for statistical analysis of measurement error structure in general, somewhere along the line you need to have a measure that you're happy to call a reference measure. Now, we have a handful of recovery biomarkers, double labeled water or urinary nitrogen for some nutrients, that people are saying, well, I'd believe that's a reference biomarker. You probably used to have people hiding in the bushes to watch what people are eating, and that for direct observation, you might consider that to be a reference measure. But a lot of times what happens is people say, well, you know what, if I'm going to validate my instrument, I have my new instrument, against something else, I'm going to validate it against some other more intensive self-report instrument. And validating is a way of looking at measurement error structure. So in a sense, you're treating that intensive self-report as a reference measure. Now, when you have this random error, that introduces what's called within individual variation. And that sort of thing can be, that sort of within individual variation, as you probably know, you can damp the effect of that by averaging several replicates. That over repeated applications, you average the standard error of the mean gets smaller and smaller and smaller, just like Stan said. Thank you. Stan, you're helping me out a lot here. But if you only average over a few replicates, you only partially damp that variation. And this is a slide showing that here's truth, the blue curve. It's very narrow, a standard deviation of only 10. When you look at a single observation that's measured with classical error, it's the distribution is much wider. Now the standard deviation is almost 30. And averaging only the mean of 4 of these daily observations only pulls you in, doesn't pull you in all the way. It pulls you in some, but not all the way. But what does that do to your epi analysis? Well, it turns out, what I've plotted here is these blue dots are true exposure, and the magenta line going through them is the line that you would get if you fit your regression through that cloud of blue points. And the slope here is 0.73, and the R-squared for that line is 0.55. Now, the red circles represent measured exposure, measured with classical measurement error. And when you fit your green line through that cloud of points, the slope is 0.43, and the R-squared is 0.35. And so what's happened is you're not getting the right thing that you wanted. Now, the intuition behind this is the following. What you're doing is you are leaving the response axis all unchanged, but you're stretching out your exposure axis. So think of like this line was on that silly putty, and you take it and you stretch it, and see it bends over and it flattens out like that. Well, what that intuition is more formally saying is that if you use Q instead of truth, it produces an attenuated slope estimate. And the expected value of that slope is the true slope, the green slope, or the magenta slope, sorry, multiplied by what's called an attenuation factor that's typically greater than 0. And because of the way this works out, your significance tests remain valid, and I'll talk about that in just a minute. But the lower R squared for the regression implies that Q, using Q, made you lose some power to detect that relationship between your exposure and your outcome. And that power loss, it turns out, and I'll show you how, is directly related to what is commonly known as the validity coefficient, the correlation rho between T and Q. So when you go to quantify this, if you happen to know the measurement error structure of your classical error instrument, in logistic regression, for example, the slope that you care about is the log odds ratio. And what we said was that the log odds ratio when you use Q is roughly equal to attenuation factor times the log odds ratio when you use T. And that means that you exponentiate and you get this sort of thing. But what this means is that the only way you're going to get an odds ratio of Q that's using Q that's 0, well, this isn't 0, so this must not be 0 either. So that's why so testing for a significant effect with Q is equivalent to testing for the significant effect if you actually had T, all things being wonderful. Now, I said there's power loss. That power loss is equivalent to a reduced sample size. You think you've got enough power to detect something because you have a big sample. Your effective sample size is actually the sample size you have multiplied by the square of this correlation, of this validity coefficient. And conversely, if you power your study to detect, to get a nominal n to say, if I could measure truth, I only need this many people, what you really need if you have an error-prone instrument is you take your nominal n and divide it by the square. Well, what does that mean in practice? Let's say we're very, very lucky and we have our choice of 3 different reference instruments, Q1 through Q3. And the only difference between them, they're both all reference instruments, but one of them, Q3, has a pretty weak correlation with truth, and the other one has a very strong correlation with truth. And it turns out for classical measurement error that the attenuation factors will square the correlation, and so you know what those are. And so basically, let's assume that you get what you pay for with these instruments, and Q1 is the most expensive and Q3 is the cheapest. How should you allocate your resources in your study? Well, if your specified increase in true intake actually increases your risk by 60%, your true relative risk is 1.6. Then the studies using the different instruments are going to estimate much smaller increases, between 4% for the cheap one and 26% for the most expensive one. You're still not getting all the way up there. You're still some attenuation, but it's a lot less with this, with the Q1, the higher correlated instrument with the higher correlation. But you plug those same numbers back into the power loss calculations that just show our equations, and you see that you actually, detecting a relationship using one of the imperfect instruments requires 2 to 11 times the sample size that you would need if you really could measure truth. So what that means is, so this is 1, this is 2, this is 4, that's 11. What that means is that one administration of Q1, the expensive instrument, is worth 2 administrations of this middle one and more than 5 administrations of Q3. So it may be a false economy to go with the cheapest per administration because you need so many more. Now also, using Q1 is more likely to give convincing evidence of a dietary effect, all things being equal. 1.25 relative risk seems to be much more evidentiary than, say, a 1.12 or 1.04, which could easily be dismissed by detractors as simply due to confounding or could arise from confounding. But that's not the only kind of measurement error there is. And the Kipnis, Victor Kipnis and Rudolf Cox model considers 3 other kinds. And 2 of them are systematic additive bias and relative bias, that additive bias applying to equally to all individuals. Systematic is a multiplicative factor for each individual's true value. Say an assay captures only a fixed percentage of the true level. And then this other one, person-specific bias, where error is not related, it is related to personal characteristics. Something about a person is going to make them over or under-report on a given instrument. And so here's I think this is probably the last equation we're going to have, so that's good. The sad part is that multiple types of error can occur together, all right? So think of this, remember I said that if you had a classical instrument that that there was no error, everything falls on that 45-degree line? Well, that's a perfectly correlated instrument. Think of this, and a correlation measures linear relationship, the strength of a linear relationship. So this is your line, and it says the group level has a straight line, but not everyone falls on that straight line. So that's person-specific bias, that no matter what happens, they're always going to be off that line. And then there's this random error that we actually like, that we can take care of by simply averaging things. And it turns out that depending upon the magnitudes of these betas and the variances of these effects in the population, you can get either unaffected slopes, exaggerated slopes, or attenuated slopes in your regression lines. And the statistical power, it might be unaffected, but sometimes, especially with person-specific bias and random error, that power gets reduced. So you need bigger samples to detect an effect. So what I want to talk about now is what I call the double whammy. So I've just told you that if you have an instrument that has this arbitrary measurement error structure, that you have this line that's not a 45-degree line, it's shifted and it's got a different slope, and there's all this noise around it. Well, what that does is you get this really attenuated slope estimate, and your exposure that you're measuring with your instrument is way off. And so your small observed effect sizes coupled with incorrect scaling of exposure means it's really hard to really interpret how much exposure do I have how much of an exposure must I change to get any kind of benefit. Okay, that's the double whammy. Even if you were lucky enough to be able to detect a relationship with the imperfect instrument because of the valid statistical testing, I said. Well, what's the current state of affairs? We got multiple cohort studies out there in the field that use FFQs as the main dietary instrument. They already have huge sample sizes for such studies because they're looking at rare outcomes like cancer. So they say, oh, well, that might be enough to detect my effects because, you should, if I get a 0.3 or 0.5 is probably pretty good, right? If I get a 0.5 correlation, I'm feeling pretty good about myself. And a lot of them actually also use a more intensive measure, either diaries or records of 24-hour recalls, and what's called a calibration subsample. And they do that thinking that statisticians will come along and use those models they've developed and use this intensive measure as a reference measure for statistical adjustment. But sadly, I don't see that happening very often. And I think I kind of know the reason why. But I'll tell you that in just a little bit. But let's go back to that first claim. How bad are things really? I showed you some hypothetical examples with correlations around 0.5, 0.7. Well, when you look at biomarker validation studies, and Larry Friedman at Gertner Institute in Israel is leading an effort to investigate error structure for FFQs and 24-hour recalls by pooling several large biomarker validation studies using these reference recovery biomarkers for energy, protein, and potassium intake. And the FFQs, and this is just from open, but there's not really many big surprises in the pooling project. These are pretty low correlations. 24-hour recall is not that much better. Protein density is getting up there to 0.4, but it's not 0.5, and it's not 0.7 at all by any stretch of the imagination. Similarly, the attenuation factors are ridiculously small for energy and protein based on FFQ. Protein density gets you up there. 24-hour recall doesn't move much at all. But that's not the whole story. That helps you figure out what your power is and what your attenuation factor might be. But looking a little more deeply into the structure, we see there's differences between these two ends of the spectrum. FFQs have a large systematic error component and a large person-specific bias component, but very small within person random error. Averaging a bunch of FFQs doesn't help you much. They're very reproducible. So the weak correlation they have with truth is all due to this person-specific bias. The systematic error doesn't actually affect the correlation so much, it affects the attenuation factor, though. But we also, the biases in the random error are reduced by energy adjustment. Taking densities is good. But you still may have power loss or attenuation that's too severe to really count on this big cohort study being big enough. 24-hour recalls, on the other hand, have a smaller systematic error, smaller person-specific bias, large within person random error, but we like that because we can just average that sort of thing and mitigate the effects. But it's not really a reference instrument. So all the statistical tools and stuff technically might not be really valid, although depending on how far away from a reference instrument for a given outcome it is, they may be robust enough to handle that. So I said a minute ago that I had an idea about why it is that a lot of these calibration studies don't get used. Well, Ronald Reagan once famously said that the 9 most terrifying words in the English language are, "I'm from the government and I'm here to help." Well, I don't really know if I buy that, but in my experience, the 10 most terrifying words in the English language are, I'm from the statistics department, and I'm here to help. So, and that's on us as a field. You know, these statistical tools and models are complicated. We might not do a very good job talking about them. We obviously don't get to leave the office very much, so we don't have a lot of interaction with the real world. But that's part of it, and I think that needs to be something that is we have to somehow meet in the middle, where statisticians have to be able to say, look, we're trying to help you keep from getting slammed by reviewers saying that your measurement error is killing your results. Okay, but we can't work magic. Okay, the measurement error corrections that have been developed by statisticians really only apply in aggregate. You can get distributions of usual intake. You can correct regression slopes, but you can't get the power back. Once an instrument's out there and you've lost power due to measurement error in the instrument, you don't get it back. It stays gone. And you can't take an error-prone instrument and use it to get a very good estimate of usual intake for a particular individual. If you need good information on a particular individual, you have to go and get that information with much more intensive effort. So is there anything that can be done? You know, is nutritional epidemiology just spewing pollution out into the field of science and it's going to cause a horrible cataclysm? I don't think so. But I think there is something that can be done to build in some improvements into the process to continue to draw from Stan's talk. First thing, you know, admit that it's there. Admit that there's standard error, that there's measurement error in your dietary instruments, or any of your instruments really. There's measurement errors everywhere. You need to be able to quantify it first before you can do anything with it. So the validity coefficient, obviously you can get that for free from your validation studies. So that's not that hard to obtain. The attenuation factor may be harder to get, but as people start saying, hey, I need the attenuation factor and the correlation. Remember, the first time I did it, I said you can get the attenuation factor from the correlation if it's purely classical error. But that doesn't hold for the more complicated models. So you need to have both these things estimated for your instrument in a validation study. And so once you know about the validity coefficient and attenuation factor and you're starting a new study, well, you can budget for it. You can build this uncertainty into your power calculations. And it may be that the cheaper instrument's not the most cost-effective after all. And you know, consider setting aside some of your money to get a calibration subsample with a reference biomarker or with a more intense self-report, and be willing to work with some of these statistical models to analyze your data and to correct for measurement error. And finally, adjust for it. The best thing you could probably do, and well, in my opinion, obviously, because it has the word statistics in it, is to bias correct your estimates with the statistical models. But I said, but even then, the statistical models aren't, you know, may not have perfect reference instruments. They may not really be valid. Well, it turns out that using imperfect reference instruments, on average, for based on error structures that we know about from these validation trials, that using imperfect reference instruments is better than just ignoring the problem. On average, you get closer to truth, you're doing the right thing, you know, repeat those studies and keep doing this sort of thing, and you're actually going to get closer to truth. It is going to require more effort, so it's not going to be as convenient as it used to be. If you can't even do that, at least admit that it could have had some impact on your results. Use sensitivity analyses to explore your what-ifs. If you can't get a calibration sub-study to actually do this hard stuff. And if you're a consumer of information, you should be taking these unadjusted results based on error-prone instruments as qualitative at best. Maybe they had enough observation, or maybe they had enough people to detect there's something going on in this axis, outcome exposure axis. But as soon as I start telling you you need to have 10 to 11 servings of whatchamajiggy to get any kind of relative risk, they may be falling into that double whammy trap. Now in the future, I think the future holds some hope. I think that there is a big push now to find better instruments new gold standard reference instruments, new biomarkers for intake that can be used in some of these things. Improved alloyed gold standard self-report instruments. 24-hour recalls, have been very, are seen as very expensive, hard to field. Well, there are people out there trying to make web-based self-administered ones that may not be, USDA is probably in the house. I want to avoid any criticism, but they might be, close to as good. If there's something about 24-hour recalls that makes them less error-prone, then doubling down on the good parts of that is worth doing. There may be some technology to the rescue where device-assisted or continuous monitoring of intake. I think Carol Boucher's done some work with having a camera to assist in your recalls. And of course, it's also on us as statisticians to develop better statistical methods, and there's a lot of work being done on that. Multivariate modeling of contemporaneous observations, where when you want to do some modeling where you have lots of confounders that are dietary, the best thing to do is to jointly model and to jointly correct for the measurement error. So there's some work that's being done in that. And also the idea of looking back and figuring out, can you combine instruments from these two ends of the spectrum? Where one is weak in one area, can you balance out that weakness with other instrument strength by combining short and long-term self-reports with biomarkers and or each other? I think there's some work being done in that, and I think that would be a very nice thing to do. So I gave you a very brief rundown on measurement error. If you want more resources and you haven't heard of this, the Measurement Error webinar series is a 12-part series, about 18 hours worth of webinars that do a much more exhaustive and in-depth evaluation of how you can account for measurement error and dietary intake data, and there's the website right there. So.